First of all, good morning, everyone. And Today, I'm going to talk about some deep learning frameworks for clinical diagnosis, and these frameworks are used in a healthcare system. So here I will explain a few of my works. So just start with this first task, like unit architectures in multiplanar volumetric segmentation validated on 3D MRI cohorts. So what we have done in this work, we started with this 3D MRI image, means 3D scan. Now, from this 3D scan, we extracted several 2D slices, right? So, another terms, you can say from this 3D scan, 3D image, we extracted the two-dimensional image, and this image has been extracted from different orientation, from different angles, right? So, in other terms, we can say from different planes, we extracted the 2D slices from this 3D image. So in this block diagram, I have shown the 6 plane. So 1, 2, 3, 4, 5, 6, like that. So now, after extracting this 2D slices, we applied a unit architecture on this for segmentation purpose. So here, in place of unit, we applied unit 2 plus or unit 3 plus, unit 2 plus deep supervised version, unit 3 plus deep supervised version. But I'm showing here only unit 2 plus because unit 2 plus accuracy is highest among all. Now, uh, after applying unit 2 plus, we got this segmented output, right? We got this segmented output corresponding to each extracted 2D slices. So this is the OAI data set. In this OAI data set, there are 7 classes, 7 different classes. So here you can see in the segmented output, there are 7 different colors, and each color is representing the particular class. Now, uh, such a way, we are going to find 6 different segmented output corresponding to each 2D slices. Now we are going to we whatever output we have received here, this output uh, will not be in correct format, means will not be in the format which we are like looking here. It will be in some rotated form, right? Because we have extracted the slices from different angles, right? So for making this architecture in a proper format, we applied nearest neighbor interpolation here. So after applying the nearest neighbor interpolation, these images will come in this format. Now we got 6 different output, but our input is the 3D scan, and here output is the 2-dimensional. But we should get the output in the 3-dimensional image only. So for that purpose, what we have done, we have merged or we have fused these different planes. So for fusion purpose also, we are doing the training. So now here just looking the different colors. These, like each color is the probability generated by the softmax activation function. Because if we are going to apply the unit, then in the classification part, we apply the softmax activation function in the case of multi-class classification. So this probability will work like an input, and we will assign some random weights here and bias, and then again we will apply the training. So that training will call fusion training. So after doing this training, we are generating the 3D output. So if mathematically we will talk, then like we have 6 planes. So here B means number of planes means 6, 1, 2, 3, 4, 5, 6, and K are the number of classes. So 7 classes, and we are generating this like 7 classes only. Now one point here, uh, we have shown you as the 6 planes, but we applied this method for 3 planes as well as for 1 plane also. But in case of 6 planes, our accuracy is highest. That's why we are focusing on the 6 planes only. So this is the way like we applied. Now here like we have just whatever I explained you. We have written like v1 to vk means k value will be 6, and like 1, 3, and 6 number of planes we are using. Here you can see how we are going to extract the slices, means 2D slices from the 3D scan. So these are the different angles we are selecting, and this is the particular one angle. Like for example, we are extracting the slice from sagittal axis. So this is showing one axis, for example, sagittal, and this diagram is the showing all the directions from which like we are extracting the slices. And if you want to see this fusion step more closely, like then we have like 6 views. On the 6 views, we are applying this fusion model and we are generating the predicted output. So for comparison purpose, we are comparing this true ground truth to this predicted output. Now, as I told you earlier, we applied this method on unit 2 plus, unit 3 plus. So and unit 2 plus supervised version, in unit 3 plus supervised version. So I'm showing only just simple unit 2 plus 3 plus here. So this method, this unit 2 plus is giving the highest accuracy because it has full scale skip connections. Like this is the encoder part, this is the decoder part, these are the medium coder part, but we have some skip connection, more skip connection here to preserve our important features. So that's why like we are focusing on unit 2 plus more. Now here like we are giving input as w cross h cross ch, we are generating output w cross h cross key. You can see here w cross h cross ch is the input, and we are generating w cross h cross k. K is the number of classes, and we applied this method on 3 data sets: OAI, CCBR, and Lyra. In OAI there are 7 classes, so that's why there are 7 different colors. In CCBR there are 2, and in Lyra we have 5 classes. So in the same way, there will be a number of classes here. Now this formula is representing the number of segmented output. So we have 6 different segmented output from different slices. So this v value will vary from 1 to 6, s1 to s6. S stands for segment. So here this output size will be w cross h cross d cross k. D is the depth and k is the number of classes. And for fusion purpose, as I told you, we are considering this PKC, generated probability from that unit model as an input for the fusion. And this one WKC and beta C, we are assigning random weight in the beginning. So now for fusion purpose, we will train this function. Now, like we applied this operation on this, like we have done experiments on 3 different data set, OAI, CCBR, and Lyra. In OAI, we have 60 scans. In CCBR, 140. In Lyra, we have 39 scans. And if you will talk about number of slices, then these are the number of slices and number of classes. And these are the different parameters generated by radiologist. And for this work, we collaborated with the radiologist in Copenhagen University, Denmark. So radiologist provided this Lyra and CCBR dataset. And this Lyra dataset has been applied first time on our method. No one had used this Lyra dataset till now. And these are the different parameters generated from a scanner. And these are the results. So our results is like significantly better than the previous one. So for all the data set, for all the 3 data sets, you can see here. So we have shown you only 3 planes and 6 planes result. 1 plane we are not showing because that result was not too good. And different parameters here for each of the model. So for MPUnit, we have a 62 million parameters, and for MPUnit 2 plus, we have 36, MPUnit 3 plus 27, like that, right? So in MPUnit 2 plus, we have like considerably lesser parameters than other one, but of course in MPUnit 3 plus, we have lowest number of parameters, but like but accuracy of MPNet 2 plus is higher than the other one. Now we have also done this pair t-test. So if we want to prove our method is better, then our alternative hypothesis true should be true. So to make this alternative hypothesis true, this generated pair t-test value should be less than 0.05. So because we are generating it at 5% level of significance. So in most of the cases, we can see our values are less than 0.05, except this few, right? So we can say MPUNet 2 plus is performing better than the existing one. And to generalize the performance of this method, what we have done, we have combined the dice score of all the three cohorts of all the three data sets, LIRA, CCBR, and OAI. So in all the three cohorts, there are only two classes, medial tibial and medial femoral, which two common classes. So we combine the dice score of only these two classes. So here you can see like this is the like Boxer and Whisker plot for medial tibial cartilage, and this is the Boxer and Whisker plot medial femoral cartilage, right? So this is for MPUNet 2 plus, and this one is for MPUNet and MPUNet. So so if you want to compare this diagram, then we need to compare first one to third one. In a first one, we have less number of outliers as compared to third one, and our mean, median, and or all the quartiles are above than this third one. In the same way, we can compare second one to fourth one. So it proves like our method is performing better than the existing one. Now these are the statistical parameters generated from this diagram. So here here also we can see our method is performing better. Now we have also done the cartilage wise performance testing. So each cartilage is also performing better, like dice score is more than 0.8 in all cases, right? So we can say each cartilage is segmented well. And we have shown the earlier we have discussed the quantitative evaluation, but qualitative evaluation is also necessary. So we have shown the performance of each slices. So this is the ground truth. Second row, second column is the generated method from MPUNet 2 plus. Then others are the existing method. So we can see like our method is more or less close to the ground truth, right? So this is the way we can prove, but like as we are working on 3D scans, so but here we have shown the output for the 2D image. So like it will be better to show the output in terms of 3D image, but it is very difficult to visualize the errors in the 3D image. So what we have done, we have calculated number of false positive from each cartilage of each cohort. And those number of false positive are mapped from 3D plane to two-dimensional plane. So in front of you, there's a two-dimensional version of 3D plane, and this plane is representing the number of false positive in each scan, in each 3D scan. So this is the average. So average means like we can say number of false positive in each scan divided by number of slices in the scan. So we can say that the average false positive in each slice. So if you will see this color map, and in an MPUNet 2 plus, if color is darker, then we can say we have a large number of false positives. So here you can see like it's a little darker than like this one, and same way other places also. So we can say we have a less number of false positive in complete 3D scan as compared to the other previous one. Same way we have done for false negative for other for the medial tibial cartilage, right? And same like for lateral tibial cartilage we have done, right? So for all the cartilage we have performed the experiment, and like in most of the cases, in all cases, we can see like MPUNet 2 plus is performing better than MPUNet. Now this is the conclusion for this work. Like we have like applied this method on 30,400 slices, and for different planes we have applied, and lots of quantitative and qualitative evaluation we have done for the performance purpose. Right now, I would like to show you some other work, because here in the conference there might be some new researcher. So if they want to start their research in a medical domain, so how they can start the research. So I will give you idea about some frameworks they can use the idea in their work, right? They can use, they can think in this way how other researchers are doing. So there's a one work that is called double unit. So in this double unit, for the segmentation purpose, what author has done, he has taken the input as a 2D slices or 2D image, 2D medical image. Then he applied this BGG19, means transfer learning technique here at the encoder part. Why he is applying the transfer learning? Because he would like to reduce the complexity of a model. So in using transfer learning, he can directly use the weights. Now he's using this ASPP to extract the features from different resolutions, from different multi-resolutions. And then he's applying some like decoder part, because in unit we have encoder part and decoder part. Encoder part is connected to decoder with the help of skip connection. So same unit he applied here, right? Encoder to decoder he connected, then he got this output. Now now what he is doing, he is taking another unit, and he is taking the output from first unit as an input, and in parallel to that he is taking one more input here, and by combining both the inputs, and he's applying the encoder, then he's applying the decoder, and he's generating the output using skip connections. And he's also using this skip connection between first unit encoder to the second unit decoder. So, and he's like concatenating, again he's concatenating the output from first encoder and the output from the second encoder, and he's generating the output. So this is the way like people are thinking, people are working, and this method is proposed by Davis in 2020. Right, so this work has been applied on a polyp data set. So this is from output 1, this is for output 2, and like it is like difficult to segment the polyp. So but we can see like it is good. We can consider it is a good category. Or like for other data set also they applied CBC clinic database. And this is the other one for lesson boundary segmentation, right? This is the quantitative evaluation here. So this is the way like people are working for medical image segmentation. Now we can see, because we have a time, then we can see one more work. That title of this work is dense Inception Unit model. So in this work you will learn how much deep a particular person can go to find the accurate model. So the architecture of this model is just like a unit, because the shape of this model is like U. But in place of simple unit, means in place of simple like convolution operation, max pooling operation, here we are applying some blocks of operation, means lots of convolution, lots of max pooling in a different way. Just see this one. Like we have an input image of size 256 cross 256, and it's a grayscale image. So our channel is 1. Now on this input image, we are applying this inception residual block, right? I will tell you in the next slide what is the inception residual block, and we are generating this output like 64. So right, so because we are using 64 number of filters here, so 64 will come the output of this one. Next, we are going to apply the downsampling block, right? So in place of max pooling, simple max pooling, we are applying the downsampling block, right? So again, we are using inception residual block, then downsampling, just like this encoder part. So, and finally at the compact layer, right, at the bottleneck layer, we are using this dense inception block, right? This one is dense inception block. And same way, we are going to apply this upsampling block, and we are doing the concatenation. And from encoder to decoder, we are using the skip connection. Now, just see about this inception residual block, what it is doing. So this is the inception residual block. You can see earlier in unit we have done only simple and simple convolution layer, but in place of simple convolution layer, here we are just taking the input, we are applying different 1x1 convolution, and like then batch batch normalization layer, right? 3x3 convolution layer, we are applying then 1x1, and this we are generating output, right? So this is the inception digital block, which will replaced by this single block. Now, same way, inception next block is also there, like dense inception block, because here you have seen this dense inception block, this one, right? So this dense inception block, like we are taking input, then inception residual block, like bottleneck layer, then inception residual block. Means this is a very complex one. Like so, and lots of connections are there in between. And this inception residual block is further expanded in this other block. So here we are using the same size of filter, 3x3 convolution, but here we are using like 1x3 or 3x1, because we want to extract the edge from horizontal dimension, or we want to extract from the vertical dimension. So these are the ways we are applying, and here you can see like downsampling block here. So it is not a simple downsampling. We are using lots of operations like input, max pooling, 1x1 convolution, right? And we are generating the output, and upsampling also, we are going the upward, right? So these are not the simple. So these are the way we are going to apply the operation. My screen sharing is paused. So like we applied on this different method, like this author applied on different methods, and he got the output in a different way, right? So these are the ways we can use the output. So that's all from my side. So I think it was helpful for you. Thank you very much. If